Uh, so welcome everybody. My name is Nombuyiselo Murage. I'm from the University of Liverpool, and I did my dissertation in conjunction with Tomoko UK Limited. And the project of this dissertation was on deriving spatial temporal geographies from mobile GPS data using a big data-driven approach. We've aptly co-named it Living Boundaries, and I think you'll be able to appreciate why. So the initial question at the beginning of my dissertation that was posed to me was very abstract. It was, how are we able to, how are you able to quantify and model collective experiences of human beings and look at the spatial and temporal characteristics of how they move around the city? And that formed into the objective of our dissertation of the dissertation, which was on modeling geographies that have been derived from user to place interactions, from collection of actual people experiences, and that to form self-organizing geographies that I'm calling the spatial temporal geographies, or whose boundaries are calling the living boundaries. So the data set that I was available to was about 1.2 billion data points, and it was generated by about 6.7 million users. And the particular approach or the appreciation of how we can appreciate a collective user experience was that we wanted to use the whole data set in its entirety as a big data approach. And key to that was to look at how we can develop a data preprocessing methodology that allows us to subset the data set intelligently, as opposed to just taking a small section of the data and applying our methodology. So a key aspect that I'll be focusing on is on the data preprocessing steps. But here's the highlight of the methodology as I move along. It was on cleaning the data, which is the outlier detection, H3 trajectory compression, and then we moved into homework leisure detection, and finally the main gist of our project, which is on spatial community detection to derive our spatial temporal geographies. So the first part, just to frame it for everyone who's dealt with GPS data. GPS data is a high frequency, high sampling rate kind of data set, and therefore you can be able to get 1.2 billion data rows covering a short period of 3 months. So the particular methodology that we wanted to do was, in order to address geoprivacy, in order to reduce the sheer subset of the data, we were converting all the GPS data points into H3 cells, such that we're able to have a low dimensional representation of our user trajectories. And our user trajectories were framed from a 24-hour period. So it's the movement of a person along a 24-hour period. And therefore, when we talk about particular user's trajectory, we're talking about them in a 24-hour window, and they are defined by a sequence of H3 cells as opposed to the actual data point. So in that regard, we were immediately able to reduce the data set by row count, and also we were able to look into concerns on privacy issues. So the objective of the data preprocessing was to be able to select stops whereby we're able to define user experience. Is that stops is a particular place where a user has spent a substantial amount of time that quantifies a meaningful engagement with that place. So that's why we were focusing on stops as opposed to just general movement of where a particular person has been. So as you can see on the screen, you can see the objective of the data preprocessing. And that was on our outlier algorithms and our H3 compression algorithm. Both of those algorithms were developed in SQL simply because of the sheer size of the data set. As I mentioned, we're looking at 1.2 billion rows, and therefore the algorithms that we were working on were developed to handle that kind of data set. And the basic principle I want to, obviously there's a lot going into it, but the basic principle of this was to sort of develop a clustering method using SQL, such that if I can draw your attention to what you have on the screen, for example, we have a user's trajectory that shows a particular stop, and we're able to collapse and compress that data set by looking at the time windows a particular user has spent in a particular grid cell. So if you should see stop one in the raw data set was represented by about that's about 9 rows in the first 9 rows, but you're able to compress that row into one row by noting the entry and exit times. So therefore, we're able to achieve some sort of data compression and also removing the data set. So the biggest achievement in terms of both practical and business objectives was that we were able to develop a complementary tool to clean the data set, and a tool that is complementary to the DB scans or the k-means clustering that was used that is used in Python, but that is applicable at using SQL and using data sets. So on average, you're able to achieve a 92.7% compression on the initial data set. And for the most part, we see like October was reducing for about a little under 500 million to 31 million, 25 and 23 million. So now we have the data preprocessing in play. The main aspect of modeling the collective user experiences was on understanding what spatial interdependence is. And spatial interdependence is defined as the connection between two places based on common set of users. So we have a relationship. A user has a relationship with a venue individually, just they visit a particular place. And then there's a relationship between that venue and another venue, this location. And thereafter, if there's a subset of these users who have visited another venue, there's another relationship. And we were leveraging on the fact that past researchers have been able to prove and show that network graph theory can be used to uncover geographic phenomena based on the network structure, that is clusters. You can use network graph theory to identify and uncover clusters. So that's what I was mentioning to you on, that the strength of identifier geographies was based on individual user to place interactions. And after those interactions were established, we were able to establish user to place interactions based on the commonality of users. And thereafter, we were able to even filter this kind of data setting according to various temporal signatures or temporal profiles. So that is the raw network graph, and it's obviously not meaningful. We have to map it a bit. So I can just quickly show you what we meant by mapping. When we mapped out our network graphs, and these were network graphs being fed by about 8 to 9 million data points, and this is what we were able to uncover or acknowledge, is that for the month of October, when we fed all the stopped data points for the month of October, we were able to understand how people move within the city in New York, and they form unique, distinct clusters that apparently actually were partly highly stable from month to month. For example, like if you see here near the John F. Kennedy Airport, there was a microcosm of like a own spatial temporal geography that formed within itself. And we had geographies that were very, very highly stable from month to month. And we're able to see that you can be able to develop boundaries, self-generating boundaries from collective user experiences. And this has a lot of applications in urban development and urban planning. And one thing that we noted is that bigger geographies mean that people in general in that particular area have to move longer distances to access certain amenities, which can tell you a lot about the quality of amenities in a particular region, how stable transport networks are, and so forth and so forth. If you want to know more about this, you can access my website here, and I also open sourced the network graph script, and yeah, the geography, the outputs of the geographies are on this link. Yes, thank you so much.
Thank you very much. Nombuyiselo, sorry if I pronounce your name wrong, but if there is a chance, I don't think some of us saw the demo because of the way your shit was slide. So if after the next presentation, there might be a chance for you to demonstrate the demo again. Before, when Nombuyiselo's demo didn't show up during her talk, and especially as she won the vote despite the demo not coming up. Jan reminded me, and it would be great if there's an opportunity now for you to show the demo to us all. How do you pronounce your name again? Nombuyiselo, is it?
Thank you. Nombuyiselo.
Thank you. Thank you. So if you can show the demo, that would be fascinating.
Okay. I hope now you can see it.
Here we are. That's right. Now I think we can see the different look at it.
Yeah. So I think just recapping on what I was saying was when you use network graph theory, you can take advantage of the community detection processes that previous researchers have uncovered and also extended further into incorporating a distance decay component. So my contribution was to further incorporate the user to place interaction component, like to take account of each and every user's interaction with a particular space. So the node I was showing you about the cluster of points, all of this relate to a particular place, and each particular place is reference to a certain grid, H3 grid. I think one of the discussion points we had during the question answer session was on geoprivacy, which is something I really needed to account for in my project, given that I was dealing with individual data sets. So we were working with grid, the Uber H3 grid library, and it is very useful in terms of highlighting geoprivacy concerns because you're able to find you're able to do your analysis, individual data analysis at a refined scale that's lower than the lowest administrative level, but higher than an area that would cause concern. So, like I was telling you, the boundaries were self-organizing, they were self-generated from each and every individual's user experience. That's 6.7 million users that generated about 1.2 billion data sets. And what we found was that there's a high level of regularity in how human beings move, both spatially and temporally as a characteristic. So over here, you find that the data for the month of October and the data for the month of November. And what that shows us is that the common set of people who moved within this region are very highly stable in this particular region as well as in November, and we saw the same in December, that the geographies were highly stable. That if I can say, like, maybe if a device or someone is detected at a particular place, then the extent to which they will move in that city is based on other people's past people experiences was this far out or this far out or this far out. The other thing that I did highlight was on that the bigger the geographies, you can infer the sense of distribution of amenities, that certain common sets of people have to move far away the geographies of which they move generally as a commonality is very big and means that there's a sparsity of amenities, which is very interesting to highlight when you talk about urban planners trying to understand how people use their city space. And other places that are highly regular that make you understand certain nuances of the city. Like, for example, in Manhattan, the geographies in Manhattan are very stable throughout all the months of October, November, and December. And it means that, first of all, the geographies were smaller, which was telling us the distribution of amenities within Manhattan was very close-knit, that for a number of people, if you took 1 million people, they wouldn't have to move far to access certain things. So in a sense, you kind of get an appreciation of why I'm calling this living boundaries, because they were generated by people's data, not as opposed to drawing it as a geographer or drawing it based on amenities. This is just 6.7 people. This is how they moved in October. This is how they moved in November and December. And you find that it becomes very highly regular. So we also did. I also did a profile for. This is the December. If you compare the December and October and December profiles, they look very similar. And like I mentioned earlier, is that there are some certain parts of the city that are very highly stable. The boundaries don't change, and that's specifically around one of the things I wanted to highlight to the audience was this geography is around the John F. Kennedy Airport. When I did some investigation underlying the maps, I saw the distribution of POIs of points of interest, restaurants, and amenities was very highly clustered, and it means that if you happen to be in this region, you don't have to move far to get access to so much of the things you want to access to. And again, Manhattan was highly stable, and Staten Island, if you're in Staten Island, you're more likely not to leave Staten Island. And it was very interesting. We also saw
I've lost your signal.
because we were looking at it at. Hello, can you hear me now? Can you hear me now?
Yeah, you're becoming intermittent at the moment.
I did share this link, and you can be able to see how the geographies manifest and move themselves from every profile, from monthly, November, October, December, weekday, weekend, and then we also had day profiles. We had day profiles of morning to midday, midday to afternoon, and afternoon to evening, and you get an appreciation of the regularity of the spatial and temporal characteristics of human movement using network analysis.
I'm very pleased you were able to show it. As many other people know, it doesn't take me long in a conversation to get around to looking at what people can understand from their networks and their graphs rather than their attributes. And so I'm a very biased observer of what you've been able to demonstrate in that what you can reveal just from people's interactions rather than from their attributes. So very good, and I think it's a very useful way of interacting with geography, and that you actually see how people really behave rather than the artifacts of the sort of geographical structures that you place on data. So it's really fascinating. So having been reminded properly from Jan and Gary the things I missed out, I'll now wrap up. So thank you very much, Nombuyiselo. That's extremely fascinating.